Welcome to the office. We want to take a look at a brief example considering what the center and the commutator subgroup of some group are. So if we want to find the center of this group, we want to notice that Z3 is abelian. So everything commutes. Okay, excellent. Within Z3 anyway. S3, on the other hand, the set of all permutations of the numbers 1, 2, 3, has only the element row naught that commutes with everything. That, of course, is the identity in S3. So that is the only element that commutes with everything. So the center of the group, Z, that's not the Z I wanted just a regular Z, the Z of G, the center of the group is equal to, let's see here, Z3 direct product with just the identity element row naught. So now as I take anything in here, I can multiply that, right? Addition in Z3, composition in S3, so I'll call it multiply is fine. Take anything from here, multiply it from anything in there, and there's no issue reordering the first entry because Z is commutative, Z3 is commutative, and there's no issue reordering row naught with everything in here because it is it commutes, right? But it's the only thing that commutes. So then I get overall that this describes the set of elements that commute in this group. That's what we're trying to get. So I took the two pieces individually and then took the direct product of those two pieces. And that's a perfectly acceptable approach. So that's the first part of what we're looking for. The other part is the commutator subgroup, and that's a little bit more difficult. Now, the commutator subgroup for an so the commutator subgroup C. Oh yes, the commutator subgroup is everything of the form A times B times A inverse B inverse. Now, in Z3, A times B times A inverse times B inverse. Well, this is commutative. It is commutative in Z3. So we actually get that this is equal to, let's see here, A times A inverse times B inverse, which is just the identity 1 times the identity 1, which is 1. Or I suppose we should use E here. E is not really what we think of, but I'm also using multiplicative notation for our binary operation here, which isn't quite right either. So, but the point is it's E. It commutes. So the only commutator is 0 in Z3 because everything commutes. So since I can rearrange everything, once I evaluate each of these expressions, A, B, A inverse, B inverse, I get back 0. 3 plus 5, well, I guess it's Z3 here. 1 plus 2 plus a -1 plus a -2. Oh, look, they all cancel out. Wonderful. It's 0. So the only commutator is 0 in Z3. Now, our text shows that the commutator is A3 in S3. And I would encourage you to take a brief look at that. It's a pretty simple and short explanation. But again, what I can do is I can take the cross product of these two things to get our commutator subgroup, because I can take things of this form, comma, things of this form in Z3, things of this form in S3, and what I'm going to get is I could take the identity, of course, and that's going to give me identity width and identity width. So anyway, cross product again is fine. So C is the cross product of 0, the identity, and let's see here, cross product of 0 because it's commutative, and A3. So we get the center and the commutator subgroup, and that's what we were looking for. Excellent. So thank you for your time. Join me for one more example, and then we can conclude the section.